Okay, so in this practical, we will implement several objectives for generative adversarial model networks. It should be easy for, especially for those of you who already tried to work with GANs, and it should be interesting for other guys. For those of you who, experienced with GANs, you can try to implement the bonus task. It's Wasserstein introspective neural networks. Basically, it's a GAN without generator, where you sample fake data using only the feedback from the discriminator and nothing more. So for now, I will now go through this notebook and give you a brief introduction in the task, and then me and my assistants who are sitting in there, we will be walking around this room and help individually. So just raise your hand if you have any question or something doesn't work, and then we will come to you and help you. So, okay. Basically, what's happening in this notebook? There is a huge cell that defines a sampler of the real data and sampling from the prior Z. Basically, you do not need to edit anything in there. Then there are some utility functions that do the visualization. Again, you do not need to edit them. Then we define the architectures for discriminator and for generator. For the first two tasks, you do not need to change architectures, but for Wasserstein GAN, you will probably need to. And how do you change it? It is described in the task. Then here comes initialization for generator and discriminator. We set our optimizers. Again, you will probably never need to change them here. And here is the main cell. It contains the definitions for G loss and D loss. It's basically the loss that you use to update your discriminator and the loss that you use to update your generator using the fixed discriminator. And that is basically where you will write your code mostly. So it will be easier for you if you use this variable task and basically do some kind of if statements, like if it's task 1 where you need to implement a regular GAN, then you return something like that, and then if it's task 2, you return different thing. Okay, so when you are done with the first task, basically, I mean, to be done with the first task, you actually need to write a single line in G loss and a single line in D loss functions. When you're done with that, you can run all the other cells, and immediately in this cell that is called train the model, you will get the animation with your GAN training actually. So please make sure that it works, and when it works, then you can go to the task 2, task 3, and so on. So that is basically it. If you now let me go through the GANs that you will need to implement. Present. Okay. So the first GAN is the regular GAN, and its game is as follows. Okay, so this is a log loss, a regular log loss that we use in classification. Yeah, and this is our objective. So make sure you see that in here we're maximizing over D and minimizing over G. Right? So do not miss with the signs. The easiest way to check that your signs are correct is to make sure that they are opposite for the generator in two cases. The first case when you learn sorry. Yeah, so basically in two cases. For discriminator, you compute gradient of this thing with the sign, with the minus sign, right? Because you want to minimize it. And for the generator, you do not put this minus sign, and so you will have very similar objective that, I mean, this term will be very, very similar, but it will have a different sign. And so this is actually the main part to check. So this term should have different signs in G loss and D loss. Okay. So this is the first task. This is the first objective that you need to implement. And the second objective, for the second objective, you need to change logarithm of 1 minus d in here to logarithm of d of g. Okay? It will change with minus, yes, actually, with minus. It will change. Yeah. There should be a minus, just read it carefully. So instead of minimizing logarithm of 1 minus d, we will need to maximize log d, which means minimizing minus log d. That will be the second task. And again, it's one-liner. If the first one works for you, then it will be easy to change the second term, and then again, without changing any hyperparameters, it should work. Now, when you are done with the first two, you can try to implement Wehrgan, so Wasserstein-Gunn. Note that it's a little bit different from this. In here, we had a classifier, so we had a sigmoid on top of the classifier, on top of our discriminator, limiting the outputs of the discriminator to 0, 1 segment. In Wasserstein-Gunn, we do not want that to happen. So make sure that you remove sigmoid from the discriminator, which is now designated as F in here. Yeah. And you need to change the objective. But that is very easy. You just apply your discriminator to a batch of real data, to a batch of fake data, and just compute the difference. Okay, what is not that trivial is to implement this Lipschitz constraint. There are two ways to do that. The first one is to restrict the values of weights, do weight clipping. It basically, I guess there is a link to a code where this weight clipping is implemented. So if you do not know how to do that in PyTorch, you can go to the link and find this place. Basically, this function is called torch.clamp. It just you know, clips the values of the in the tensor to a specific range, and we want to clip them into a range, for example, from -1 to 1, or from -0.1 to 0.1, something like that. You probably need to experiment with that, or even 0.01. It is the task 3, and in task 4, yeah, it's the wrong number here. Task 4 is Wgun with gradient penalty. Gradient penalty is tricky to implement yourself, because I mean it's technically difficult. So you can find a link to GIST where this gradient penalty is already implemented. So just read it carefully and insert this piece of code into the right place. Okay. For both variants of Wgun, the objective stays the same. It's written in here. What is changing is the way that we constrain our discriminator to have this Lifshitz property. And if it's very easy for you, then you can implement Wasserstein introspective neural network. This is basically a generative model that is very, very similar to WGAN in a sense that you also have gradient penalty, but what's different is that you do not have a generator at all. To generate samples from the fake distribution, you actually run sampling process using Langevin dynamics. So basically, if someone starts to implement that, and I suggest you just open the link with the paper, go to the algorithm, read it, and just implement, because it's rather straightforward. All the caveats are written in the description, so after some time it should work for you quite well. So, okay, now if you have any problem, please raise your hand, and some of us will get to you and we will solve it. So I was talking about like looking for the algorithm in the paper about Wasserstein introspective neural networks, which is this bonus task. For all the other tasks, if you do not know what to implement or how to implement, it's better to raise your hand, and we will discuss it. Please pay attention that there is one cell that you execute at, and it draws you like a square with some arrows and so on. It's just a cell that shows an example of visualization. You need to run the next cell with the training model, and there will be a kind of animation. So what does the arrows mean in that plot? It's basically the gradient that the discriminator pushes to the generator. At every kind of point, we show with the arrows the gradient for the generator, how the points should move, how the discriminator thinks the fake points should move. Yes, and another issue in that cell where you do training, if you run it, you will encounter an error. You will need to insert pass word in the if statement in there.